if I have a bit of a blob of ink on a piece of white paper and I put my thumb down on that ink, I just get a smudge. But if instead I take a pen, I can take exactly the same amount of ink and draw a beautiful diagram if I'm a good artist. And my contention is that is what nature is doing. It is spreading out energy and creating structure.
Julian, it's great to see you. I checked, it's been almost a decade, which gives me some sense that maybe time is some kind of an illusion. And having been sheltered for months where Wednesday seems the same as Sunday, time no longer seems to be flowing in my life. So I'm almost becoming a believer in your radical theory of time. In all seriousness, though, I have read your new book, The Janus Point, The New Theory of Time. And I was immediately struck by the vastness of your vision. Last time we spoke, we were focused on time, which was radical enough in terms of your approach. But now, from that, you've built a really remarkable superstructure that engages virtually everything. So what I'd like to do to begin is give you my sense of the major ideas that you have. And then you go through it, correct me, we want to get the overview, and then we want to go into each of the pieces to give the justification, or at least the reasons for the speculation. So let me start, and I have roughly 5 points. First, that time does not flow, and it does not have a single direction past the future. Second, the history of the classical universe is a succession of shapes. It's an important word in your work, shapes, from which the notion of duration, of what we may think is time, emerges. 3, the history of the universe is not one of increasing disorder, which of course is the traditional and conventional wisdom in science, increasing entropy, but rather, you say, of the growth of structure. So we're going to need to talk about structure. 4, you have what you call a new vision of the Big Bang, which is, you define as the Janus point, because time then flows in both directions, the Janus being two faces. It flows in two directions from the Janus point, and it's driven by, you say, the expansion of the universe and the growth of order, whether it's galaxies, planets, or life. And then the fifth and final point is that you challenge the conventional wisdom that the universe and all reality is headed for heat death, which is not dying by heat, it's the death of heat, so that there's a very bleak future where nothing can happen because everything is totally homogeneous. And as a result of challenging that, you say, therefore, life can expand without bound, which is a remarkable statement, and it contradicts virtually everyone else that I know. So how did I do with the overview, and give me your sense?
Well, I would say that's a fairly good overview. I would just put in a caveat at the end about life going on forever. The important word is can, or perhaps one even should say could, because that's really, in speaking in normal terms, that's the very distant future, and really all sorts of things could happen before we get there, speaking in conventional terms.
Sure, but we could have a big rip or all sorts of things that people talk about, understood. But the fundamental point is that the universe is not heading inexorably, without any possibility of change, towards this elimination of heat, or what's called heat death, where everything is totally homogeneous. And once that happens, nothing interesting can happen anymore.
That's quite correct. My belief is that there's no need for variety to stop increasing. Variety can go on increasing forever. That is entirely possible.
So that's a super important point, and it flies in the face of pretty much all of our mutual colleagues and their views, which I know you take as a compliment, not a criticism.
Well, it's not quite against everyone. People a key thing in this is the question of ratios. Quite a lot of modern cosmologists do say that there won't be heat death, but what they say is that the density of energy will decrease. But all that we ever are aware of really is contrast, is densities, different brightnesses. I mean, as I look at your face, one side of it is brighter than the other, and I noticed a difference there. So if there is always variety in that sense, that in some places intensities are greater than other, even if the overall intensity is going down, there is still some reality there. There is variety. This is the key thing. If there were no variety, we would not be able to think about anything. We could not have any sense of science. So it's variety that's the crucial thing, and that depends upon ratios, not upon absolute values.
Okay, that makes sense. But if the trend is towards this homogeny, then take, at the asymptote, take it out as long as you can. Eventually, it will depress the capacity on a continuing basis to create variety, and eventually become zero.
By no means necessarily. I mean, you can go on creating differences all the way. Just think about ordinary real numbers with their decimal expansion. The decimal expansion can go on forever. So there's always going to be a difference between one decimal place and the next one, so to speak. So well, you could have you could imagine two real numbers looking at their decimal expansion as you go along. There's always a difference between them. So there's absolutely no reason for variety to be killed off just because one's got an idea of an intensity. I think a lot of the problem comes from not thinking about the entire universe. All around us, we see measuring rods and clocks, and we think they are absolute. But there can't be a measuring rod outside the universe. We have to look for measuring rods within the universe. And if the things we take to be measuring rods, there are some that are so long as that, and there are other ones that are that long, there'll be a difference between them. Even if you might imagine that they're all getting smaller, but that difference remains. It's that ratio that is always the one that counts. 2 is always less than 3.
Your analogy to the real numbers and how they work it supports your point, but I wonder, is there a fundamental difference between the abstract quality of numbers and the reality factors of matter? For example, we talk about the Planck lengths. And so as things get smaller and smaller, if they hit a hurdle, call it a Planck length or whatever, that changes the physical dynamics. And so the analogy to the abstract numbers to physical matter is not direct.
It's not direct, but we don't really know what happens at the Planck length. At the moment, the Planck length is ultimately determined really by the frequencies of the cesium atom, because that's the key thing in metrology. Yeah. And we don't really know what happens to, I mean, certainly cesium atoms don't exist down at the Planck length, that's for sure. So it's uncertain. I mean, the fact is, all scientific data ultimately come in the form of numbers. And if there are differences between numbers, if there are ratios, then there's meaning. There is always meaning in ratios.
Okay, so let's do this. Let's go through each of the points that I've put together as sort of the big categories that you have, and give me a sense of why these things are true. I think everything I said contradicts the conventional wisdom. There are people, I'm sure, who agree with you, but so each of these points. Let's start with your concept of time, that it doesn't flow, it does not have a single direction past the future. This is something you've worked on for decades and are in fact a world standard on this, but let me hear it afresh.
So the first point about time not necessarily flowing in only just one direction. First of all the known laws of nature, at least all the ones that could possibly count in determining what is called the arrow of time, they are they don't make a distinction between the direction of time. The laws work the same way in both directions. And this has been the great mystery really since the discovery of the laws of thermodynamics around 1850. So, but what people always thought about, I think the key thing in all of this that is why people have not realized the proper way to think about this is that the laws of thermodynamics were discovered through the behavior of steam engines. And a steam engine must keep the steam in the cylinder box, in the cylinder. And so I say that all of the conceptualization of all of these issues has been for steam in a box or a system in a box. And a system in a box behaves completely differently from one that is not. You can, I mean, people say you start off with shall we say, a drop of liquid in the corner of a box. That is a very low entropy state. If it's in the box, the liquid it might even be a little bit of ice initially. The ice will become water, the water will evaporate, and the water molecules will spread out over the whole box. That's the classic story of the increase of entropy. Mm-hmm. However, if there is no box there and that ice is out in space and it melts, it will behave in a completely different way. It will expand out. In fact, actually, what it typically does is expand like an expanding universe. But if at the same time these atoms can interact gravitationally, they would cluster together and form structures. And this behavior in Newton's theory of gravity was already clearly recognized in 1772. And when that happens, if you just look at Newton's theory, as long as the energy is not negative, so zero energy or positive energy, you find that the system grows in size in both directions of time. There's always a minimum size where the system is most uniform. The distribution of the particles is most uniform, and in both directions, the structure grows. So this aspect of Newton's theory, nobody has recognized it, although it was discovered in one of the most important papers by the mathematician Lagrange in 1772. And it was that insight, actually, as recently as 2012, which made me realize this could be the explanation of the arrow of time.
The approach that you're using on this is the fundamental difference between a confined space and a space that has no bounds. It's not clear to me why to that individual space where that kernel of ice is evaporating, why that's different than the closed box. At some point it will, but initially it would be the same. It depends how big your box, your conceptual box is.
Well, yes, actually, in the initial stage of the ice melting and the water then evaporating, it is actually rather like that happening in empty space. And it would look initially like an expanding universe, but it's the box that is so important. That is where the idea that entropy is bound to increase eventually comes.
Right.
That doesn't change at all.
So you have introduced a new concept called entexy, if I pronounce it properly, because I never.
Entexy, yeah.
Entexy. Okay, get my emphasis in the right place. And you define this kind of the opposite of entropy because it's something that it kind of helps create structure, or it decreases it. It's sort of everything you thought about entropy and turning it upside down.
That's quite correct. And I think it's, the people have said for a long time that gravity is anti-thermodynamic, because if you start off with a uniform distribution of matter subject to Newton's gravity, the system will clump, this is the phenomenon I'm talking about. And to save the second law of thermodynamics, everybody is so determined they must save the second law of thermodynamics. It cannot be violated. They say gravity is anti-thermodynamic, and it increases when the entropy under gravity increases. But I'm saying, actually stop and think. Actually what it's doing, it's becoming more special. I mean, I mean, if you look around the universe, it looks very special. It doesn't look disordered at all. I mean, the mere fact that we can talk to each other, we can
Right.
go out with telescopes and look at these fabulous galaxies and things. Does that look like disorder? Tell it to the Marines, is all I can say.
Look, I loved your analogy because the typical a way to describe in lay terms the expanding universe is a balloon that's expanding, and so dots on the balloon get further and further apart as the expansion occurs. But you characterized it as coins, which are solid and immovable, that are kind of pasted on the balloon. So within the coin, there is structure, and there's no disorder there, even though those coins may be getting further and further apart.
That's quite true. The thing that it all comes back to ratios. The ratio, if you take the diameter of the coin and divide it by the distance to the next coin, that decreases as the universe, in the normal terms, as the universe expands. That's when people say the universe is I was on a radio program with the Astronomer Royal in this country, and I said, frankly, the expanding universe stinks. It's not expanding, it's changing its shape, which is what it's doing. That is the only objective truth. It is changing its shape. This is all that the astronomers observe.
So that's your second big point, that the history of the universe is a succession of shapes. And these shapes, the relationship between them, is what gives us duration and then our sense of time?
Correct. And there's also no shadow of doubt that these shapes are getting more structured and more interesting. I mean, there's no shadow of doubt that when you go back near to the Big Bang, the universe looked very uniform, and it's been getting less and less uniform and more structured, at least up to now. What might happen in the very distant future, we cannot say with any degree of confidence, but we know what happened up to now.
Let me give you the traditional argument that that you need to undermine that explains that. And that says that while the overall universe is indeed increasing in entropy, so that the second law is maintained, locally, that because of the flow of energy, like from the sun to the earth, there can be structure, plants, people, or whatever, but that's drawing the sun's energy. So it's a local concentration that increases order and structure, which seemingly contradicts the second law, but no, it doesn't really, because the energy that it's drawing from outside more than makes up for that.
That's the conventional way of looking at it, but there is another way. A thing that I think is very important is what William Thomson, who then became Lord Kelvin, said in 1852. He had a very significant paper which he titled "On a Universal Tendency in Nature to the Dissipation of Mechanical Energy." And this is the sort of story. Now, he said he had chosen the word dissipation because he did not mean that energy was being destroyed. Only the creator could do that. What he could have said was that energy is spreading. Now, if energy is spreading, that doesn't mean to say that structure is being destroyed. The image I give right at the end of my book is if I have a blob of ink on a piece of white paper and I put my thumb down on that ink, I just get a smudge. But if instead I take a pen, I can take exactly the same amount of ink and draw a beautiful diagram if I'm a good artist. And my contention is that is what nature is doing. It is spreading out energy and creating structure. And you can see a beautiful example of this. It's been raining a lot in this around here in the last few days. I walked down to a stream where the water flows over a shallow water flows over a ford, and water drops fall from the tree into the water. So there's energy concentrated in that drop of water as it falls into the water. But when it does that, beautiful circular rings spread out. So that is your spreading of the energy, which was all concentrated in the thing. Right. And it's created that beautiful picture. And you have lots of drops coming down, and all those circular waves pass through each other. They don't destroy each other. They pass through each other So actually, you can sit there and watch it for hours, and it's a very beautiful effect. That is energy spreading. That, I think, is the right way one should talk about the second law of thermodynamics when you haven't got a system imprisoned in a box. That drop of water is not imprisoned. It is eventually because there's the banks of the stream. But if this was a still ocean, those waves could go on forever.
Well, they could go on forever, but there's some attenuation of over time.
There's attenuation, but not necessarily of the ratios, because bigger ones will meet smaller ones, and when the bigger ones meet smaller ones, there's always a difference. What you need is difference to talk about science.
So your characterization, which is what I had your point 3, that the history of the universe is not one of increasing disorder, but rather of the growth of structure, whereas the conventional wisdom says that, yes, there is the growth of structure. That's obvious. You can't deny that. But it is because of the differential in the universe in different segments of it, but still there's an overall disorder. So that is a crucial point, because everything that you project, speculation, of course, everything you project is dependent upon that fundamental point. Is that right?
Can you just, could you repeat the point? You
Sure,
say that the...
Sure. I may not repeat it the same way the second time.
No, that doesn't matter.
The fundamental aspects of your big speculations, your big idea, is based on the fact that the increasing growth of structure is a fundamental part of what I think you call the law of the universe.
Absolutely, yes.
Big idea, this big idea. That's the important thing. Whereas conventional wisdom says, yes, we see the growth of structure. Of course we do, but that is because we are in local areas drawing on the energy of the totality, and therefore in other areas the entropy is still increasing. So the overall sum is still towards disorder over time, but locally there is this growth of structure because of this differential. So what I'm saying is, and you've explained that, but that is the fundamental idea that undergirds your totality.
Yes, I mean, can I just say something a little bit about black holes? Because this was the famous discovery of Stephen Hawking, that when black holes form, a huge amount of matter is concentrated in a very small region. But that is actually changing the structure of the universe. It's putting a lot of matter in a very small space. We know, we've seen this marvelously, when two black holes merge, it's just like that drop of water falling into the water. The gravitational waves spread out. It's just unbelievable, the information that is constantly streaming over the Earth with the details of what is going on right back to very close to the Big Bang.
Right, they're milliseconds. That very thing.
We can pick it up here, and the lower the more we go down in the energy that we receive, we still go on picking up details. I mean, these radio telescopes now are picking up energy densities that are unbelievably low, but they're still picking up all this fabulous structure and a picture of what the universe is like. I mean, it's tremendous.
Let's go to the Big Bang, because you have a definitely a new vision of it. This is your Janus Point, in which you say time flows in both directions, or two directions from that, driven by the expansion of the universe or the growth of structure. So take me through that.
So first, I should say there are two possibilities that what happened at the Big Bang, or the Janus Point. One is that talking in the conventional way, the size of the universe does not go to zero. This is the situation that Lagrange discovered in 1772. Then you just have a situation where effectively there are two universes with opposite directions of time. There is one point where, in the conventional way, the size of the universe is its least at the smallest value, and the distribution of matter is most uniform. And in both directions away from it, the matter clumps, the structure grows. That's the picture if the universe does not go to zero size. Possibly much more exciting is when it does go to zero size, and it may be even there that my Janus point idea may be challenged. This would depend on exactly how quantum gravity comes out in the end. It may be that there is actually just one point, one very special shape of the universe, and out of it all possible shapes emerge bit by bit, as it were, from a single point, a single shape, which I call alpha. Now that's an idea which actually developed as I was writing the book. It might even undermine the title of the book. But either way, the problem of I think either way, whichever possibility turns out to be the better one, there is an explanation of the arrow of time, that mystery of why everything flows in the same direction. If the size is non-zero, then there is these arrows pointing in its opposite directions, and the symmetry is respected. All the solutions have the same symmetry. If the size goes to zero and this more radical idea is correct, then the universe will have a unique beginning. The law of the universe says it must start in the most uniform state that is absolutely possible. And from then on, variety will go on increasing forever. Each successive shape will have a greater variety.
So I can appreciate the concept, and I see obviously our side of the Big Bang where time flows in the direction we're familiar with. Flows as I'll put in quotes. But what happens on the other side? The other side, you say structure also is developed as time goes in the opposite direction. How does that work?
First of all, anybody like you and me who can talk to each other, they're going to be on one side or other of the Janus point. Right. And for them, for each side, time will seem to flow forward in exactly the same way. I mean, one just analogy, I mean, imagine that you and I went to the top of Mount Fuji in Japan, and we walked in opposite directions down that beautiful mountain. As we go down, we find the landscape and the vegetation changing progressively as it goes down. And essentially it will change in exactly the same way for each of us. So as we go down in our separate ways, we can't talk to each other. We can't shout over the top of Mount Fuji. And we just find that the world changes in exactly the same way for us. So if by any chance we could then speak on the phone, we would say we've had exactly the same, or qualitatively the same experience.
You know, I love the analogies that you use here and in your book. I mean, they're very rich and they're very meaningful, and of course they do support your vision. But I always have to wonder that there seems to be a vast gulf between these human-related macroscopic analogies and what we're talking about in terms of the universe. There's so many bizarre things, from quantum mechanics to size and everything else. But the analogies are great, and you know, so I like them a lot.
Yeah. Well, what I will say is I think they are. It amazes me. I think they are actually almost the first time anybody has spoken like this. To me, it is an amazing fact that people have just not questioned that box in which thermodynamics was discovered. So much came out of thermodynamics, including after 50 years, the discovery of quantum mechanics. It was critical, that box, the theory all assumed that the atoms and the molecules bounced elastically off the wall of the box. And that led to, they confirmed the existence of atoms and molecules, their sizes, and eventually they discovered quantum mechanics. That is absolutely amazing. And people were so amazed by that, and it seemed absolutely inevitable that the second law must be absolutely true. And nobody has questioned that. I search every time I look at what people have written in books, in scientific papers. I have not seen one single person questioning this assumption that the system is in a box.
Well, this also relates to this enormous contradiction that you talk about, which says that the universe had to begin with very high order, very low entropy, and then has been going through this progressive degradation through the inexorable effect of the second law of thermodynamics. And yet all around us, there's the growth of structure. And what some people have done, Roger Penrose in particular, and he's a friend of all of ours, and we wish him great congratulations for his long awaited Nobel. So that's great. But he talks about, and he even comes up a number, the level of order in that he has to have in the early universe is like 10 to the 121st power, which is 121 zeros. The number doesn't have a name. It's so large. But so he has to come up with that in order to play out the traditional structure, and you don't need to do that. Is that right?
Well, my position that I've put in the book very hesitantly, well, I hope respectfully, because it's two very great scientists, is that both Richard Feynman and Roger Penrose may have got to the right answer, but with the wrong argument.
Yeah, you take on the biggest and the best.
Yes, well, no, I mean, I think it's absolutely clear. There's this famous theorem that Poincaré proved in the early 1890s called the recurrence theorem, that basically if you have a system which is got to be in a box, then it will always come back to the state that it was in once before, arbitrarily closely. Mm-hmm. And if you look carefully at the arguments that both Feynman and Penrose do, underlying that is the assumption that the universe is in a box. It's quite clear in Feynman, and it's also, if you look carefully in Penrose, when he comes up with that estimate, that fabulous number, basically he's assuming, it's a critical point in his first book, The Emperor's New Mind, that the universe recollapses, it doesn't expand forever. And that's what enables him to come up with an estimate. He assumes that all the matter in the observable universe collapses into a black hole. He estimates the entropy of that black hole using Hawking's formula, and that's what leads him to this absolutely colossal number. But pretty well all the evidence at the moment, most cosmologists now are convinced, think there's strong evidence the universe will go on expanding forever. So I think that strongly undermines Penrose's argument. Nevertheless, that the universe would start off with a very uniform special state, that was always very likely, going right back to this paper of Lagrange in 1772, that it would be, there would be a most uniform state in the past. So I think that the conclusion is correct, but the argument is wrong.
Julian,
I can't answer back, but Roger might he's only 25 miles away. He might get a bit annoyed with me.
Julian, what I'd like to do now is subject your grand vision to some of the questions and issues that are extant in cosmology, in physics, and even in psychology or consciousness. And ask you the big question. What I want you to do, this is not easy, but I'm gonna give a concept. And if we're assuming that everything you've said is true, that time doesn't flow, that there's this Janus point, that the universe, the second law doesn't apply as people have thought because the universe is not a closed system, that ratios and shapes are what's important, all of that together, I agree 100%. Now, if that's true, what happens to each of these things? How do you interpret them? And I'm going to give you, take 20 seconds or 30 seconds for each one. That's the challenge here. All right, here we go. So if everything you said is true, what is the Big Bang?
The Big Bang, I believe, is the most uniform state that the universe can have. And it just begins in the most uniform shape. And at least up to now, that variety, that shape gets richer and richer. And that is actually in agreement with what we see, what the astronomers tell us.
Next, inflation theory. That's a theory that that what gave rise to the Big Bang. Prior to the Big Bang was this enormous increase in the expansion of the universe within a very short amount of time. Uh, Exponential increases, people with different numbers, 10 to the 50th or whatever. Alan Guth, Andre Lindy, others have contributed to this. So if what you say is true, what happens to inflation theory?
This is a conjectural part of my idea, but what they were really, the real triumph of inflation is to explain why the early structure in the universe had the form that it did. And that is undoubtedly a great success. As of now, there is no serious rival to inflation. What is rather intriguing, and there are diagrams in my book, which at least in Newtonian theory suggest that if the universe comes out of a situation where the size is 0, it will come out looking very uniform, but not exactly uniform. And in fact, actually somewhat looking, when you look at the pictures, looking like the sort of structure that inflation is put there to explain. So the suggestion is there is an alternative to inflation, which is completely different, that the universe starts off looking very uniform, but not exactly uniform. And the deviation from exact uniformity, just as in inflation, then leads to all the structure we observe. If from very primitive, from very precise first principles, we can say the universe must start with certain seeds, it must be very uniform, but not exactly uniform, and the departure from uniformity is the same as in inflation, then we have an alternative theory, and we might be able to make much more precise predictions.
How about quantum gravity, the holy grail of unifying quantum theory with general relativity?
Well, I put in a page and a half in the book where I make a conjecture about that. And one of the really big problems in quantum gravity is what is the nature of time? And the key mathematical concept in my book is what I call complexity. Complexity is just a measure of the variety of the universe. And people have made various suggestions for what is time. And I'm suggesting that time is that complexity is time. Time is literally the complexity. So you can look at all the possible shapes of the universe and put them all together, those that have the same complexity. Some will have more complexity than others, but there will be a whole lot that have the same. There will be a unique one where the universe starts. That has the least complexity and the greatest uniformity. But after that, there will be lots that have the same complexity, but are different shapes. And the quantum theory of the universe is about what are the probabilities for those different shapes. So this is actually a very precise theory. It's entirely possible it's wrong, but I believe it is actually the simplest and clearest, and in some ways the most logical one that's been proposed so far.
I was actually impressed by that. I don't know if I agree, but I was impressed. Okay, let's go on. Creation of the universe ex nihilo, from nothing.
I would say no. I would say it's there forever. I mean, the possible. When it comes to mathematics, I'm quite Platonic. I'm hugely impressed by things like Pythagoras' theorem and so on. I think that there are just possible shapes. I mean, probably the most important shape in the whole of mathematics is the triangle. I mean, in Euclidean space, all of trigonometry, the complex numbers, everything comes out of a triangle. So you can have all. For me, these triangles exist in eternity. They are there in all times. So I don't believe in creation ex nihilo. Here I agree strongly with Roger Penrose and Max Tegmark. I think there is, so to speak, a Platonic realm of mathematical structures, which somehow or other we do experience.
How about creation of the universe, but the special birth conditions of that initial condition?
Well, they are just there. The space of all possible triangles, there is one triangle which is very special. It's the equilateral triangle. So this is my point alpha. if the universe just had three particles in it, the Big Bang would be the equilateral triangle. And we would be somewhere where we're looking a bit like a shard, with one side much shorter than the distance to the two distances to the other particle.
How about the large scale structure of the universe?
Well, I've explained that with the idea about inflation, that the universe starts off with the most uniform, but not completely uniform. There are seed non-uniformities at the, that's not true in the equilateral triangle, except that the equilateral triangle, if you're in Newtonian gravity, the particles can have different masses. That introduces a certain amount of variety. And as soon as you get any number of particles, a few hundred, you have a lot of very interesting structure when you get to the most uniform possible shape.
How about defining what you call the law of the universe, and why is it that such exists?
That, of course, is a complete mystery. Although,
well, let's start with this. What is what you call the law of the universe?
I conjecture that the law of the universe is that it begins with the most uniform shape subject to a certain criterion. So that I define a quantity called complexity, for which there are strong mathematical arguments to take it seriously. The complexity has the least possible value. If it's just three particles, it's an equilateral triangle. If it's many particles, it's very interesting, but it has a very definite structure, and it's a very uniform, but not completely uniform. And from then on, you just get all of the possible shapes of the universe arranged successively at different times, which is just, their time is just how complex they are. But at a given time, some have more interesting structure than others, although it's the same complexity. And that complexity just goes on increasing. So the advance into the future is just the increase of that complexity.
How do you undermine the conventional wisdom that we are headed for a barren universe?
Because the variety never gets washed out. It's to do with the importance of ratios. As long as there are differences between, I mean, think of Gulliver's Travels. You can do all sorts of things once you've got things of different size. As long as there are different sizes, there's reality, there's possibility for sensible existence.
Okay, now I'm going to get a little bit broader, move away from pure physics. And how about the concept of teleology? Most physicists, as you know, would say that the universe is what it is. And Steven Weinberg's famous remark that the more we understand the universe, the more we see how pointless it is. But some have pushed back against that more recently, about that there may be some teleology built into it, which is usually a curse word in science.
That's quite true. I touch on that a bit cautiously in my book. I have to admit that the suggestion that the universe starts off in the most uniform way it possibly can, but with some seeds of non-uniformity, variety, and goes on getting more varied, that does look teleological. And in fact, actually, it's not far removed from what Leibniz said. Leibniz said he says we live in the best of all possible worlds, but actually, if you look carefully at what he really said and believed, he said that we live in the most varied of all possible worlds. Mm. And actually, a great scholar in Leibniz, I haven't yet managed to check it out and find the place where it is in Leibniz, but he told me Leibniz had two ideas: either that the universe is always in its most varied state possible, or that the variety, it is always increasing, the variety. So this case would be exactly actually what Leibniz had conjectured over 300 years ago. Yes, just over 300 years ago.
You venture into the swamp of consciousness and the hard problem of how we understand our experience, subjective experience with physical matter.
Yes, I I just can't do any better on consciousness than what William James and quite a lot of other people, it goes back before that, if we believe in an external world, and I certainly do believe in a structured, mathematically structured external world, I just have to assume what's psychophysical parallelism. What I experience, there is a counterpart in the external world. We can find a structure out there that matches what I experience. And Galileo says this very clearly back in 1623.
That's not saying the same thing, though, that our consciousness so-called supervenes that's on the physical world. A parallelism is different than supervening, where one is totally dependent on the other.
To be honest, I think this is still so difficult. Actually, I wish I knew much more of neuroscience, because I think neuroscience may be beginning to tell us very interesting things. I mean, I'm sticking my neck out enough with what I'm saying. I'm not going to pretend to tell neuroscientists what they're discovering, you know.
Sticking your neck out is one of the core principles of Closer to Truth. So we're on solid grounds here.
Okay, good. Yeah,
so if what you say is true, how do you look at the word forever? What does that mean?
That I don't think any conscious being is going to live forever. I think that's a rather alarming thought. I mean, personally, I've had a wonderful life. I'm already 83. It looks as if I've got a few more years of good quality of life, but I'll settle for early 90s and not complain. No, but it may well be that completely different form of awareness, I would prefer to use awareness, will be out there in the future. And of course, we don't know. There might be awareness all around us of which we have no knowledge. I mean, in some senses, we know that trees and fungi underneath, are communicating. There's no question there's communication. To what extent you could call that awareness, I don't know.
Let's look at some of the two maybe biggest questions that your work might impinge upon. And one is the existence of a traditional God, whether in the Western personal sense or the Eastern more cosmic consciousness sense. If everything you say is true, are there any implications to the existence of such supernatural kinds of foundational entities?
I think, if what I'm saying is going in the right direction, I think it's too early to say. I'm agnostic. I was brought up a Catholic. I rejected the Catholic dogma in my teens. Then I met someone who told me to read Jesus's the New Testament seriously. I was very impressed by Jesus's ethical teaching. I think some of it is very beautiful. Things like the woman taken in adultery, let he that is without blemish cast the first stone. For me, my ideal of how I would like to live is that I remain otherwise agnostic. And I've had a hugely rich life. I'm immensely grateful for the life I've been able to enjoy. In my first popular science book, I said, being here is the supreme gift. And it still holds true for me.
How about what we at Closer to Truth say is the biggest question of all? Why is there anything at all? And if I hear what you've said, if the universe didn't have a beginning or it had this movement in both directions towards this original point, whether it's a zero or close to zero, does that answer the question, why is there anything at all? Because the answer is that it was always there by brute fact.
Well, this is where I come into my sort of Platonic ideas about mathematics. I do, just to take another example from mathematics, 5 and 7 are prime numbers. And they just seem, that seems to be some truth that is there. And I don't think 7 will ever cease to be a prime number. And so to that extent, it seems to me there is eternal existence. There is eternal existence of at least of possible structures. And I can't go any better than that.
Julian, the progress in your ideas over the last 9 or so years since the last time, call it a decade since we met, if you have that same progress over the next 10 years, I want to schedule right now another session just like this and see where we've come.
Oh, well, thanks very much. If these tentative ideas I have about quantum gravity are right, it might be worth it, but they are tentative. They are tentative. But it will be wonderful if they're, because it has all sorts of fascinating possibilities. That page and a half that I put at the end of chapter 18 of my book, if they come out right, that's going to be exciting.
Thank you for watching. If you like this video, please like and comment below. You can support Closer to Truth by subscribing.